So thank you very much for the introduction, and thanks for the organisers for inviting me to talk. I always enjoy coming to Melbourne. It's a nice, quiet backwater from where I normally live, which is the futuristic metropolis with really cool tech like the light rail system and drone delivery systems. It's the drone capital of the world, Canberra. So about a year and a half ago, I live on the outskirts of Canberra. All these drones started buzzing over my house, and I wondered what was going on. And it turned out that a company was doing a drone delivery trial in our sort of area of Canberra. So I quickly got the app and tried to find out whether I could get deliveries to my house, but unfortunately there were too many trees and power lines and things. So my neighbours, I could actually see the drones flying over my house and then dropping the donuts or the coffee onto their front yard, and then they came out and they picked up the donuts and went inside and ate them. And sometimes it'd be just like this continuous stream of drones over my house, dropping food and other delicacies to them. So it was really frustrating that I couldn't get deliveries. So I thought, well, why don't I just build my own virtual drone delivery system? Unfortunately, it's not real. So they gave me the inspiration for this demonstration application about a year and a half ago. My background is universities, R&D, labs, CSRO, NICTA, and a startup company. And 6 years ago, I started working for Instaclustr, which is based in Canberra. So that's sort of a bit of background. Let's get into it. So Instaclustr provides a managed platform. It's a cloud platform for big data open source technologies. And a recent addition was for workflow orchestration with Uber's open source Cadence. So Uber actually developed this as part of their Uber Eats business for delivering food. So there is actually a connection to the delivery story. And this talk is about Cadence. And I've also thrown in Kafka and more recently TensorFlow as well into the stack. So we provide managed Cadence and Kafka. TensorFlow is something that you would have to run yourself. Workflow orchestration is pretty simple in terms of the concept. It's really just about task ordering. So you start a workflow, you perform a task, and then you perform another task, and then you stop. But actually it's a bit harder in practice. That's why you need something like Cadence. So pedaling with a high cadence, or pedal revolutions, is called spinning. So you want to be spinning your workflows really fast, basically. Cadence is horizontally scalable. The number of workflows is essentially unlimited. How does it do this? Well, it's quite clever. It uses the event sourcing model to efficiently save the workflow state. And Cadence is also fault tolerant. So workflows can and will fail, and then you can recover them. Again, using the event sourcing model, you basically replay the event source history to get to the actual state at the point of failure and then continue from that point on. Cadence workflows are code, so it's quite powerful. You can write workflows in a couple of different languages. I use Java. Here's an example of a workflow implementation of 2 tasks executed sequentially. Here's the overview of the Cadence architecture as we provide it in our managed service. Basically, at the back end, there's either the Cassandra or the Postgres database that handles the persistence of the state and replaying the state upon failure. Kafka and OpenSearch are optional at the back end for enhanced visibility. We provide the managed Cadence servers, and then there's an API that you can connect to with your client and worker code, which runs the actual workflow logic at that point. But you don't need to worry about anything on the back end at all. We just make sure that it all runs magically for you. Cadence activities are quite important. Activities including, say, backwards cycling can fail. Activities are core to Cadence. Remote calls in particular can fail, so you have to wrap them up in activities. They can contain any code. Activities are executed at most once and can be automatically retried on failure. There's a few restrictions around them though, because they must be deterministic. So what are some good use cases for Cadence? Well, when you've got hundreds to millions of running workflows, long-running activities, sleeping and scheduled tasks are all a good fit. Anything where there's state fault-tolerant applications running, where there's a lot of complexity, integration with unreliable external systems, or integration with streaming and event-based systems, for example, Kafka. On the other hand, where you've got very, very long workflows, say thousands of steps, this may not be a particularly good use case because the replaying of the history can actually take a fairly long time. So short workflows are best. Some example domains that we've seen are used in our financial, retail, and, not surprisingly, delivery. So spinning your drones, here's a brief overview of the drone delivery application that I built last year. From the drone perspective, there's basically a bunch of workflow steps. The drone starts out being charged, ready to go at a base. It gets an order to deliver. It flies to an order location and collects the order from a shop. It then flies to a delivery location and drops the order off at a customer, and flies back to the base and recharges and then repeats. So here's an example of a perhaps pirate drone delivery flight. There's 3 legs to the flight, basically the base to the order location where the shop is, from the shop to where the customer is, and then back to base again. So that's more or less what the drone spends its life doing. In order to do that, it has to know where it is and where it's going and where it should be going to next. So the main complexity is in terms of the waypoint flight calculations. So this is a simulation, but I'm doing all the calculations required for a real drone. So this is an example of the returning to base leg. The drone flight path is computed inside a Cadence activity. It's using location, distance, bearing, speed, and charge data, and it does the computation every 10 seconds. If there's a failure, then the drone actually won't crash and will continue flying from the last location because activities are resilient. Here's an overview of the whole system using some swim lane diagrams to try and explain what's going on, because it does get a bit complicated. There are 2 workflows. Here's the first one, it's the drone workflow. Basically, the drone starts, it's ready, it waits for an order, it does the movement activity calculations, it recharges, and then repeats again. However, there's another workflow. Orders are also stateful. So they are modeled using Cadence workflows as well. Orders basically start, they generate a location, which is the shop location essentially. They get ready for the drone, they update locations from the drone when they get picked up, and then they end if they are delivered successfully. So that's the second workflow. Now that we've got 2 workflows, there's actually another requirement, which is coordination between the workflows. And to do this, we use another feature of Cadence called asynchronous signaling, and that enables you to get 2 workflows to actually talk to each other in an asynchronous way using signals. So that works pretty well as well. However, just to make the story a bit more interesting and also to explore how you integrate Cadence with Kafka, I decided to add Kafka to the system as well. So integration with Kafka adds starting a workflow from Kafka, and secondly, using a Kafka microservice to coordinate the drone and order workflows. So just an overview of how the system actually works. I'll just briefly go through all the steps involved in a single order. First of all, a customer places an order. You assume they've got an app or something. That results in an order being sent to the Kafka new orders topic. Step 2, start new order workflow. Basically, the Kafka consumer gets the order. It starts the new order workflow using a Cadence client. Step 3, the order is ready for drone pickup. And this is done inside an activity. Basically, it sends the order ready message to the Kafka order ready topic. Step 4 is inside the drone workflow. Again, it's in an activity. It sends a drone ready message to the drone ready topic. And the Kafka consumer gets an order ID and sends the signal back to the drone to start the order pickup. Step 5 is in the drone workflow, and it's where it's actually flying to pick up the order from the shop. So it does the computation and flies to the order location and picks up the order. Step 6, again in the drone workflow, it flies to the delivery location this time, and that's also done inside an activity where it does the calculations. Flies to the delivery location, drops the order, and also at the same time, it's sending location updates to the order workflow every 10 seconds. So that's so that the the order knows where it is at all points in time, and also potentially, say, the customer might be able to track the order delivery on an app or get an ETA for when they can expect the order to be dropped off. Step 7 in the drone workflow, again, flying back to base, also done inside an activity. Flies to the delivery location, and eventually it ends up flying back to base again and recharging when back at base and getting ready to start the whole cycle again. Meanwhile, inside the order workflow in step 8, there's an activity or a step in the workflow there which does the location update all the time. So it's receiving state and location signals from the drone workflow. It updates the state of the order, and eventually, if the order is delivered successfully, then the workflow is ended. So that's an overview of the system. My background is performance engineering. I'm really interested in performance and scalability, and one of the advantages of Cadence is the scalability. So we set up a system to see what sort of throughput we could get and what capacity and resources we needed to get lots of drones flying at once. And here is the test cluster that we use. It's not a particularly big cluster, but it's big enough to get some representative results. Cassandra is the biggest part of the system that had 18 cores. The client-side code had 8 cores, and the Cadence system itself was actually only 6 cores. So the most demanding part of the system really is the database side. So the results of the load test, we managed to get 2,000 drones running concurrently with that setup, but for each drone there's actually an order, so that's 2,000 orders as well, which gives us a total of 4,000 concurrent workflows running for that system. So that's not a bad number of things. Trying to get that number of drones flying at once in reality might be a bit tricky, as with the recent example of some of them falling out of the sky. So here's a visualization of only 20 drones flying using my backyard in Canberra as the drone base. I've sped this up quite significantly. I'll just start it up now. So the purple blob is the base location. The black blobs are the moving drones. Orange-coloured blobs are the shop locations. The red blobs are the delivery location. And they then change to green when there's been a successful delivery to that location. Okay, so there's a lot going on here. And one of the things I thought about that could be quite interesting to try and predict from the data is which shops are going to be busy ahead of time so that the shops can basically get ready and have enough people on hand to make sure they can cope with the number of deliveries expected and the arrival of all the drones and things like that. So yeah, so that's all happening in the magic world there. Okay, so the next part of the story, let's check how much time we've got. Yes, right, is Kafka combined with machine learning, and in particular TensorFlow. So this is learning over spatio-temporal drifting streaming data, which is quite complicated potentially. And interestingly enough, related to the previous talk, there is a problem of bias in this problem space. So there's a connection to the previous talk. So the goal will be to predict which shops will be busy in advance. So there's a not busy shop and there's a busy shop. So real-time machine learning is basically everywhere now. TikTok's a particularly good example. Apparently they try and optimize people's addiction to the platform by giving them exactly the sort of content they want, and cat videos are apparently a thing that are very popular. I wouldn't know, but that's a thing apparently. So the incremental learning challenge itself is a big data problem. There's lots of data. It's fast data, there's streaming data, and new data is constantly arriving. It's changing data, so there's basically this underlying problem of concept drift. The underlying rules can be changing, basically. It's just-in-time learning. It's continuous learning. The model must be as up-to-date as possible all the time for it to be useful. And streaming data is basically infinite. You can't assume access to all past data. There's maybe too much of it. So the drone learning problem in particular, you've seen the drone delivery system. It generates massive amounts of spatio-temporal data. The drone order data is actually sent to Kafka. So can we learn how to predict which shops will be busy in an hour's time? Here's the overall of the machine learning architecture. Basically, I've bolted Kafka on to the end of the order workflow. So it's sending data about successful order deliveries into Kafka. Then I do an hourly aggregation over that data and determine features like busy and not busy, which is the category we're going to be learning over, and that's then sent to TensorFlow via Kafka. And I've actually, so the aggregation is actually done by Kafka streams in my sort of demo system. Neural networks, they're sort of everywhere. They've actually been around since the 60s, and there's a cat connection here, I guess, as well, if you understand the identification of the letter C standing for cats. Neural networks are quite useful for incremental machine learning, as they actually have that sort of built into how they work, how the training works for neural networks. A lot of other machine learning frameworks don't really allow incremental learning. So TensorFlow is a particularly sensible choice, I thought, to use for this. Basically, the rest of the talk's a bit experimental. This is what I tried, and the outcomes, some of it was sort of successful, some not so successful, and I'm still not really sure of the final result yet. So it's probably a bit of an ongoing project to get the final results. So the whole process was incremental, like the learning itself. So here's experiment one. It was basically using still batch data only with no drift at all. There were 6,000 samples a week, and this is the number of samples resulting from the aggregated data. The actual number of raw samples was a lot more, but I ended up with 6,000. That's not a very large number for doing machine learning over. It's on the very small end, basically. The class was shop busy or not busy per hour. The class and features are computed from hourly aggregated delivery shop data. Other features include the weekday, the shop type, and average delivery time, and a few other things I just threw in to make it a bit more interesting. Time is quantized to hours, location to suburbs. I'm sort of cheating a bit. It's got prefix determined quantized space and time units built in, really. And the actual rule is a combination of the shop type, the location, the weekday, and the hour. The steps to train and use TensorFlow are these. There's quite a few of them. They're all relatively straightforward in and of themselves, but by the time you sort of get to the end, you have to keep your fingers crossed that they all worked and that you're getting sensible results. In step 8, basically every time you call the fit method, it actually updates the model. So that's the critical part for incremental learning. You're not relearning from scratch, it's actually updating the model with the batch data that you're giving it at that particular point in time. Yep. Okay, so in terms of evaluation of the model, what matters? Well, accuracy is a common metric that's used to evaluate machine learning models. However, it can be misleading unless you've got roughly equal positive and negative samples. So confusion matrix is slightly more useful because you can see whether there's any bias in terms of false positives and false negatives in the result as well. So the initial results I was getting from 1 week of drone delivery data with shop busy, not busy, with a 50-50 split, was not too bad. The training accuracy improved from 0.5, which is just purely guessing, to 0.88 over 125 epochs. The evaluation on the confusion matrix was pretty good. There weren't many false positives and false negatives, so that was a good outcome. However, the results were not really all that repeatable. The accuracy varied from 0.5 to 0.9, depending on a whole bunch of random things, apparently, and the training time actually changed from 5 to 92 seconds as well. So it was pretty sensitive to things like the batch size and other sort of parameters that you have to set in TensorFlow. So I wasn't really sure that I knew what was going on. The other problem is sometimes it just gets stuck in a bad local minima, which is a well-known problem with machine learning as well. So that led to a second experiment, which was actually doing some incremental learning, but sort of fake incremental learning. I didn't use Kafka, and there was no concept drift in this case. The goal is to do continuous model training from streaming data. With incremental learning, you don't need all the data at once. I wanted the model to be up to date all the time, and it's really useful for real-time use cases. And in theory, it should be able to cope with concept drift in the data eventually. So this experiment had the same data as the previous one, but with incremental learning. So the approach used was to slice the data to get 100 samples at a time. This was essentially simulating what would be happening with the Kafka poll, and then you fit with each sample And I used a batch size of 8 and 20 fixed epochs for this result. And then I evaluated against all the previous data. So there's a few funny things here which aren't perhaps ideal. The results were pretty good. The accuracy, as you can see in this graph here, improved with time. So the x-axis on all these graphs is time. The y-axis is accuracy. So the maximum accuracy achieved was quite comparable with the batch learning, but you'll notice that it oscillates. So what's going on here? I don't know yet, we'll see. I'll reveal that in a minute. So experiment 3, incremental learning using Kafka. So this time I actually put Kafka into the architecture. So the results were better. There was not as much oscillation, but the accuracy overall was worse. So it was about 0.72 compared to 0.9 compared to the batch data. And experiment 4, this was incremental learning with Kafka, and I also introduced the concept drift here. So we introduced concept drift at the start of week 2. So basically the assumption is that the shops being busy or not busy changed after a week. So the rules have changed after the end of the first week. So the second week of data has the concept drift compared to the first week. So the best accuracy during week 1 was 0.7. Oops, that's 2 minutes. Okay. The accuracy instantly drops when the concept drift hits the machine learning model, but then actually improves by the end of week 2 again. So that's not too bad. But we've still got this oscillation problem. So a couple of different variations on this experiment. The first one is where we tried resetting the model. So after we detect concept drift, we just reset the model, just completely start from scratch again, and retrain using only the new data. So this does remove the pre-drift model inertia, and it helps immediately with the accuracy of the model, which jumps up to 0.9. But there is still oscillation, and you get the accuracy dropping to 0.7 by the end of week 2. So the real question, though, is why are we getting this oscillation? Well, it turns out we actually had accidental concept drift all along. So even though the rules themselves weren't changing within each week, the data was changing over time because we had temporal features in the rules. Basically, the day of the week and the time of the day were used to determine whether the shops were busy or not busy. So that was essentially a problem. There's a timer bias fixation going on here. Incremental learning may result in a temporal bias due to fixation on recent samples. And you get a model overfitting as well, which is essentially what's indicated by the oscillation. On time series data in particular, it's a well-known problem, and it sort of leads us into this rabbit hole where we're not quite sure what's going on some of the time. Well, can we fix it? Well, just to prove that was what was causing the problem, I got rid of time. This isn't a real fix. In the real world, you do have to deal with time. But I actually removed time from the rules, and this is the final result with the reset model. There's a big drop in accuracy initially, but you get an improved result by the end of week 2. So in a production system, you could actually use multiple models. You could continue using the old model until the new one is trained up, potentially. And just some conclusions to wind up. Incremental learning is pretty fast. It should be able to keep up with streaming data in a production system. Incremental learning is able to keep the model up to date, more or less, in conjunction with resetting, potentially. The model accuracy may oscillate due to the presence of time features, fixation on recent data, changes in sample class distribution over time, and concept drift. Overfitting on time series data is something to watch out for and to try and take action to prevent or mitigate. Maybe use multiple competing models concurrently is one solution. And there's an interesting potential here to use the Cadence workflow system itself for the ML ops, actually using it to train the model and decide when to reset the model and when to apply different models and things. So that's an interesting possible use case for Cadence as well. But basically, spatial and temporal bias is inevitable. We are stuck in a particular point in space and time. It's just the nature of reality and physics. You're never going to have access to future events. Prediction of the future is intrinsically hard. But given these sorts of tools like Cadence and Kafka and TensorFlow, at least we've got some tools in our bag to try and explore some of these possibilities. And feel free to try us out. You can use all of these technologies on our managed platform. We've got a trial of 2 weeks. And there's lots of documentation, and all of my blogs are at that link there. I've got about 100 blogs on different use cases for open source software that I've written over the last few years, including the blog series that this talk was based on. So there's a lot more detail on that. I've skipped over some of the more interesting stuff and some of the more detailed parts for the talk. But yep, if there's any questions, thank you very much.